Welcome to CS 101 Scientific Python, Lecture 20, the second part of our series on optimization, when we start talking about heuristic algorithms, beginning with greedy algorithms. In numerics brute, we wrote that the goal of a brute force search is to search the domain for the x star, which yields the optimum f of x star. The problem is that most domains are far too large with too many parameters to realistically explore exhaustively. So today we're going to talk about identifying when a problem is a good candidate for a heuristic solution, or one of these non-brute force solution methods we're going to propose. And we're going to apply a hill climbing heuristic optimization technique, or a greedy technique, to optimize a 1D problem. For instance, consider the problem of cracking a password. If each character can take one of 86 characters, digits, letters, and special characters, then the brute force search looks like this. For one character, our search space is 86. For two characters, we have to try 7,396 different combinations. For a computer, no problem. For 3, it becomes 636,000. For 4, it becomes 54 million. For 5, it becomes nearly 5 billion. This blows up fast. For 10, we're trying 2 times 10 to the 19th. For 20, 5 times 10 to the 38th. Let's put this in numbers of time rather than numbers of specific operations in computing. We're going to assume that a password attempt takes 1 times 10 to the negative 7 seconds. And we're going to see how long it takes to solve each of these cases. So by the time we get to 4 characters, it takes 5 seconds. By the time we get to 5 characters, it takes 8 minutes. By the time we get to 10 characters, 1.9 times 10 to the 14th seconds, 6 times 10 to the 6th years. So 6 million years to search for 10 characters, assuming 1 times 10 to the negative 7 seconds per attempt. Now there's parallelization and other techniques you can use, and maybe our assumption of 1 times 10 to the negative 7 doesn't remain true for every system. But the problem gets big fast. By the time we're talking about 20 seconds, we're talking about a process that takes much longer than the time that the known universe exists. So clearly, breaking a password by brute force techniques becomes unmanageable, which is why most passwords are broken by social engineering techniques, wherein someone is tricked into giving someone else their password, rather than someone simply trying to crack their password. In most cases, we have to settle for what we're going to call a good enough solution. This means that we may not have found the global optimum, but it means that we found something local that's good enough to solve our problem. A lot of engineering, unfortunately, boils down to this kind of solution. We don't know the actual ideal alloy composition for making skin on an airplane wing. So we have to settle on a good enough solution, even from a design perspective, much less from a supply chain and manufacturing perspective. If we have a figure of merit, or what we'll now call a figure of relative merit, we can classify candidate solutions by how good they are. This is one way in which the password operation, while good for illustrating how large the brute force search space becomes, is not a good all-round example. Because when you check a password, it simply tells you true or false. It doesn't tell you how true or how false a particular answer is. So these heuristic algorithms don't guarantee the best solution, but they're often adequate, and indeed in most cases they're the only option we have available.